My alarm cut me off, so let's go ahead and continue. This is Openstax Contemporary Mathematics, Chapter 3, Section 1, continued. Step 2. After factoring the 7, the factorization is 10,241 equals 7 times 1,463. Oh no, sorry, Step 3. After factoring the 7, the factorization is 10,241 equals 7 times 209. Which equals 7 squared times 209. The number 209 is not divisible by 7. Step 4. Check the next prime number, 11. 11 does divide 1,463. Okay, yeah, so I think that meant to say 209. I think that's a typo. Step 5. After factoring the 11, the factorization is 10,241 equals 7 squared times 11 times 19. Since 19 is prime, the prime factorization of 10,241 is complete. We see that 10,241 has 3 different prime factors, 7, 11, and 19. Your turn 3.14. 1. Find the number of different prime factors of 180. Video. Finding the prime factorization of 168. Tech check. Using Wolfram Alpha to find prime factorizations. The Wolfram Alpha website is a powerful resource available for free to use. It is designed using AI so that it understands natural language requests. For instance, typing the question, what is the prime factorization of 543,390, gets a rather quick answer of 2 times 3 times 5 times 59 times 307. So if you want to find the prime factorization of a number, you can simply ask Wolfram Alpha to find the prime factorization of the number. Finding the greatest common divisor. 2 numbers often have more than one divisor in common. All pairs of natural numbers have a common divisor of 1. When listing the common divisors, it's often the case that the largest is of interest. This divisor is called the greatest common divisor and is denoted GCD. It is also sometimes referred to as the greatest common factor, or GCF. For instance, 6 is the greatest common divisor of 12 and 18. We can see this by listing all the divisors of each number and, by inspection, select the largest value that shows up in each list. The divisors of 12, 1, 2, 3, 4, 6, 12. The divisors of 18, 1, 2, 3, 6, 9. It is easy to see that 6 is the largest value that appears in both lists. Example 3.15. Finding the greatest common divisor using lists. Finding the greatest common divisor of 1,400 and 250 by listing all divisors of each number. Solution. We create a list of all divisors of 1,400 and of 250 and choose the largest one. The divisors of 1,400 are 1, 2, 4, 5, 7, 8, 10, 14, 20, 25, 28, 35, 40, 50, 56, 70, 100, 140, 175, 200, 280, 350, 700, 1400. The divisors of 250 are 1, 2, 5, 10, 25, 50, 125, 250. The largest value that appears on both lists is 50, so the greatest common divisor of 1,400 and 250 is 50. Your turn 3.15. Find the greatest common divisor of 270 and 99 by listing all divisors of each number. Listing all the divisors of the numbers in the set will always work, but for some relatively small numbers, the set of all divisors can become pretty big. And finding them all can be a chore. Another approach to finding the greatest common divisor is to use the prime factorization of the numbers. To do so, use the following steps. Step 1. Find the prime factorization of the numbers. Step 2. Identify the prime factors that appear in every number's prime factorization. These are called the common prime factors. Step 3. Identify the smallest exponent of each prime factor identified in Step 2 in the prime factorizations. Step 4. Multiply the prime factors identified in Step 2 raised to the powers identified in Step 3. The result is the greatest common divisor. Example 3.16. Finding the greatest common divisor using prime factorization. Find the greatest common divisor of 1400 and 250 by using the prime factorizations. Solution. Step 1. Find the prime factorizations of the numbers. The prime factorization of 1400 is 2 cubed times 5 squared times 7. The prime factorization of 250 is 250 equals 2 times 5 cubed. Step 2. Identify the prime factors that appear in every number's prime factorization. The common prime factors are 2 and 5. Step 3. Identify the smallest exponent of each prime identified in Step 2 in the prime factorizations. The exponent of the common prime factor 2 in the prime factorization of 1400 is 3, and in the prime factorization of 250 is 1. The smallest of those exponents is 1. The exponent of the common prime factor 5 in the prime factorization of 1400 is 2, and is in the prime factorization of 250 is 3. The smallest of these exponents is 2. Step 4. Multiply the prime factors identified in Step 2 raised to the powers identified in Step 3. This gives 2 times 1 times 5 squared. 2 to the first power times 5 squared equals 50. The greatest common divisor of 1400 and 250 is 2 times 5 squared equals 50. Notice that the answer matches the one we found in example 3.15. Your turn 3.16. Using prime factorization, determine the greatest common divisor of 36 and 128. Example 3.17. Find the greatest common divisor using prime factorization. Find the greatest common divisor of 600 and 784 by using their prime factorizations. Solution. Step 1. Find the prime factorizations of the numbers. The prime factorization of 600 is 2 cubed times 3 times 5 squared. Prime factorization of 784 is 2 to the 4th times 7 squared. Step 2. Identify the prime factors that appear in every number's prime factorization. There is only one common prime factor, 2. Step 3. Identify the smallest exponent of each prime from identified in Step 2 in the prime factorizations. The exponent of 2 in the prime factorization of 600 is 3. The exponent of 2 in the prime factorization of 784 is 4. So the smallest exponent of 2 is 3. Step 4. Multiply the prime factors identified in Step 2 raised to the powers identified in Step 3. This gives 2 cubed equals 8. The greatest common divisor of 600 and 784 is 8. Your turn 3.17. Using prime factorization, nice. Determine the greatest common divisor of 120 and 200. People in mathematics. Srinivasa Ramanujan. Figure 310. Srinivasa Ramanujan. Credit goes to them, and it's just a photo. Black and white photo. Ramanujan was born in southern India in 1887 during British rule. He was a self-taught mathematician who, while in high school, began working through a 2-volume text of mathematical theorems and results. His work included examination of the distribution of primes. He eventually came to the attention of British mathematician G.H. Hardy. During one visit, Hardy mentioned Ramanujan that his taxicab number was 1729, remarking that 1729 appeared to be a rather dull number, to which Ramanujan responded, "It is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways." Tech check. Using Desmos to find GCD. To find the GCD of a set of numbers in Desmos, type GCD parentheses first underscore number, comma, second underscore number, ... close, and Desmos will display the GCD of the numbers as the numbers are typed. Nice. Video. Using Desmos to find the GCD. Applications of the greatest common divisor. The greatest common divisor has uses that are related to other mathematics, reducing fractions, but also in everyday applications. We'll look at 2 such applications, which have very similar underlying structures. In each case, something must divide the groups or measurements equally. Example 3.18. Calculating floor tile size. Suppose you have a rectangular room that is 570 centimeters wide and 450 centimeters long. You wish to cover the floor of the room with square tiles. What's the largest size squared tile that can be used to cover this floor? Solution. Using squares means that the length and width of the tiles are equal. To ensure that we are using full tiles, the side length of the square tiles must divide the length of the room and the width of the room. Since we want the largest square tiles, we need the GCD of the width and length of the room, or the GCD of 570 and 450. Step 1. Find the prime factorizations of the numbers. The prime factorization of 570 is 2 times 3 times 5 times 19. The prime factorization of 450 is 2 times 3 squared times 5 squared. Step 2. Identify the prime factors that appear in every number's prime factorization. The common prime factors are 2, 3, and 5. Step 3. Identify the smallest exponent of each prime identified in Step 2 in the prime factorizations. The exponents of 2 in the prime factorizations of 570 and 450 are 1 and 1. So the smallest exponent for 2 is 1. The exponents of 3 in the prime factorizations of 570 and 450 are 1 and 2. So the smallest exponents for 3 is 1. The exponents of 5 in the prime factorizations of 570 and 450 are 1 and 2. So the smallest exponent for 5 is 1. Step 4. Multiply the prime factors identified in Step 2 raised to the powers identified in Step 3. This gives 2 to the first times 3 to the first times 5 to the first equals 30. The GCD of 450 and 570 is 30, so the largest size squared tile that can be used to cover the floor is 30 centimeters by 30 centimeters. Your turn 3.18. You are designing a brick patio made of square bricks 5 centimeters thick, but you need to determine the width and length of those bricks. The patio will be 400 centimeters by 540 centimeters. What are the largest size squared bricks that can be used so that you do not need to cut any bricks? Example 3.19. Organizing books per shelf. Suppose you want to organize books onto shelves, and you want the shelves to hold the same number of books. Each shelf will only contain one genre of book. You have 24 sci-fi, 42 fantasy, and 30 horror books. How many books can go on each shelf? Solution. Since we want shelves that hold an equal number of books, and a shelf can hold only one genre of book, we need a number that will equally divide 24, 42, and 30. So we need the GCD of the number of books of each genre, or the GCD of 24, 42, and 30. Step 1. Find the prime factorizations of the numbers. The prime factorization of 24 is 2 cubed times 3. The prime factorization of 42 is 2 times 3 times 7. The prime factorization of 30 is 2 times 3 times 5. Step 2. Identify the prime factors that appear in every number's prime factorization. The common prime factors are 2 and 3. Step 3. Identify the smallest exponent of each prime identified in Step 2 in the prime factorizations. The smallest exponent of 2 and 3 is in the factorizations is 1. Step 4. Multiply the prime factors identified in Step 2 raised to the powers identified in Step 3. This gives 2 to the first times 3 to the first equals 6. The GCD of 24, 42, and 30 is 6. So the largest number of books that can go on a shelf is 6. Your turn 3.19. There are 3 gym classes. The number of students in the classes is 21, 35, and 28. What is the largest team size that can be formed if the teams from every class must have the same number of students? Video. Applying the GCD. Finding the least common multiple. The flip side to a divisor of a number is a multiple of a number. For example, 5 is a divisor of 45, and so 45 is a multiple of 5. More generally, if the number A divides the number B, then B is a multiple of A. This drives the idea of the least common multiple of a set of numbers. A common multiple of a set of numbers is a multiple of each of those numbers. For instance, 45 is a common multiple of 9 and 5, because 45 is a multiple of 9, 9 divides 45, and 45 is also a multiple of 5, 5 divides 45. The least common multiple of a set of numbers is the smallest positive common multiple of that set of numbers. So least common multiple is LCM. There are at least 3 ways to find the LCM of a set of numbers, and we will explore 2 of them. One way is to create a list of multiples of each number in the set, and then identify the smallest multiple that appears in those lists. Example 320. Finding the least common multiple using lists. Find the LCM of 24 and 90 by listing multiples and choosing the smallest common multiple. Solution. Create a list of the multiples of each number. Step 1. The first 15 multiples for 24. 24, 48, 72, 96, 120, 144, 168, 192, 216, 240, 264, 288, 312, 336, 360. Step 2. The first 15 multiples for 90. 90, 180, 270, 360, 450, 540, 630, 720, 810, 900, 990, 1080, 1170, 1260, 1350. There is one multiple common to these lists, which is 360. So 360 is the LCM of 24 and 90. Your turn 320. Use lists to find the LCM of 12 and 15. The second method we can use is to find the prime factorizations of the number in the set to build the LCM of the numbers based on the prime divisors of the numbers. The LCM can be built from the prime factorization of the numbers in the set in a similar way as when finding the greatest common divisor. Here are the steps for using the prime factorization process for finding the LCM. Step 1. Find the prime factorization of each number. Step 2. Identify each prime that is present in any of the prime factorizations. Step 3. Identify the largest exponent of each prime identified in Step 2 in the prime factorizations. Step 4. Multiply the prime factors identified in Step 2 raised to the powers identified in Step 3. Example 321. Finding the least common multiple using prime factorization. Use the prime factorizations of 24 and 90 to identify their LCM. Solution. Step 1. Find the prime factorization of each number. 24 equals 2 cubed times 3. 90 equals 2 times 3 squared times 5. Step 2. Identify each prime that is present in any of the prime factorizations. The prime numbers present in the prime factorizations are 2, 3, and 5. Step 3. Identify the largest exponent of each prime identified in Step 2 in the prime factorizations. Prime, 2, 3, 5, largest exponents, 3, 2, 1. In that order, respectively. Step 4. Compute the LCM by multiplying the prime factors identified in Step 2 raised to the powers identified in Step 3. The LCM for 24 and 90 is 2 times 2 times 2 times 3 times 3 times 5, which equals 2 cubed times 3 squared times 5 to the first, that equals 360. Your turn 321. Use prime factorization to find the LCM of 20 and 28. 322. Finding the least common multiple using prime factorization. Use the prime factorizations of 36, 66, and 250 to identify the LCM. Solution. Step 1. Find the prime factorization of each number. 36 equals 2 squared times 3 squared. 66 equals 2 times 3 times 11. 250 equals 2 times 5 cubed. Step 2. Identify each prime that is present in any of the prime factorizations. The prime numbers present in the prime factorizations are 2, 3, 5, and 11. Step 3. Identify the largest exponent of each prime identified in Step 2 in the prime factorization. So we have prime 2, 3, 5, 11, largest exponent 2, 2, 3, 1, respectively. Step 4. Compute the LCM by multiplying the prime factors identified in Step 2 raised to the powers identified in Step 3. The LCM for 36, 66, and 250 is 2 times 2 times 3 times 3 times 5 times 5 times 5 times 11, which equals 2 squared times 3 squared times 5 cubed times 11 is 49,500. Your turn 322. Use the prime factorization method to find the LCM of 150, 240, and 462. Oh man, super burp. Excuse me. Damn. Using lists for 3 or more numbers, particularly larger numbers, could take quite a bit of time. Frequently, as in this example, the prime factorization process is much quicker. In practice, you can use either listing or prime factorization to find the LCM. Example 323. Finding the least common multiple using both methods. Find the LCM of 20, 36, and 45 using lists and prime factorization. Solution. Use listing. List the multiples. So for 20, we have 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220. 36, 72, 108, 144, 180, 216, 252, 288, 324, 360. And 45, 90, 140... 45, 90, 135, 180, 225, 270, 315, 360, 405, 450, 495, 540. The smallest value that appears on all the lists is 180, so 180 is the LCM of 20, 36, and 45. Step 2. Find the prime factorization of each number. So 20 equals 2 squared times 5, 36 equals 2 squared times 3 squared, and 45 equals 3 squared times 5. Step 3. Identify each prime that is present in any of the prime factorizations. The prime numbers present in the prime factorizations are 2, 3, 5. Step 4. Identify the largest exponent of each prime identified in Step 3 in the prime factorizations. So prime, 2, 3, 5. Largest exponent, 2, 2, 1. Step 5. Compute the LCM by multiplying the prime factors identified in Step 3 raised to the powers identified in Step 4. The LCM for 20, 36, and 45 is 2 squared times 3 squared times 5 equals 180. Both listing and prime factorization produce the same result. The LCM is 180. Your turn 323. Find the LCM of 18, 24, and 40 using lists and prime factorization. Video. Finding the LCM. Tech check. Using Desmos to find the LCM. To find the LCM of a set of numbers in Desmos, type LCM parentheses first underscore number, comma, second underscore number, dot, 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 close, and Desmos will display the LCM of the numbers as the numbers are typed. Video. Using Desmos to find the LCM. Applications of the least common multiple. Some applications of LCM involve events that repeat at fixed intervals, such as visits to a location. Other applications involve getting things to be of equal magnitude when using parts that are different sizes. See example 325, for instance. In each case, we may be looking to determine when two processes line up. Example 324. Determining scheduling overlap using the least common multiple. Two students, Yao and Amelia, meet one day at an assisted living facility where they volunteer. Yao volunteers every 6 days. Amelia volunteers every 10 days. How many days will it be until they are both volunteering on the same day? Solution. If we list the days that each student will volunteer, it becomes clear that we could solve the problem using the LCM of 6 and 10. Yao will be assisted at the assisted living facility 6, 12, 18, 24, 30, 36, 42, and 48 days later. Amelia will be at the assisted living facility 10, 20, 30, 40, and 60 days later. The smallest number appearing on both lists is 60. Yao and Amelia will once more be volunteering together 30 days later. Your turn 324. The Sun, Venus, and Jupiter all line up on a given day. Venus orbits the Sun once every 255 days. Jupiter orbits the Sun every 4,330 days. We'll ignore the decimal values of days for each orbit. How many days will it be until they line up again? Example 3.25. Determining the minimum height using the LCM. A team building exercise has teams build a house of cards as high as possible. However, the cards for different teams are of different sizes. Team 1 uses 10 cm by 10 cm cards, while Team 2 uses 8 cm by 8 cm cards. What is the minimum height when the two teams will be tied? Ignore the width of the cards. Solution. This is an example of where we want to put together objects with different sizes. We want to know the minimum height when they are tied, or when the houses of cards line up the first time. The heights of the towers built using the 10 by 10 centimeter cards will be 10, 20, 30, 40, 50, 60 centimeters tall. When the 8 by 8 centimeter cards are used, the tower will be 8, 16, 24, 32, 48, and 56 centimeters tall. The smallest number appearing on both lists is 40. The first time they are tied is when the two towers are 40 centimeters tall. Your turn 325. In an internet giveaway, every 130th person who submits a survey receives $250, and every 900th person receives a free cell phone. How many submissions must be received for the first person to receive both prizes? Video. Application of LCM. Work it out. Prime number life cycles. Cicadas. Cicadas are known to have life cycles of 13 or 17 years, which are prime numbers. Why would a prime number life cycle be an evolutionary advantage? To figure this out, we have to explore how common multiples work with prime numbers. Make a conjecture regarding the LCM of a prime number and another number. Test this conjecture with a few examples of your own making.